In this video, we're going to look at the responsive members to axial loads. We start with axial loads because they're the simplest, and a lot of the concepts that apply to pre-stressed members with axial loads we can extend to pre-stressed members with flexure and under moments and under applied moments and axial loads. By the end of this module, I want you to be able to use compatibility, equilibrium, and material constitutive relationships to relate load to stress, stress to strain, and strain to deformations. Differentiate the locked-in pre-stressing strain between pre-tensioned and post-tension members. Calculate initial strains, stresses, and deformations in an axially post-tension member. Calculate locked-in strain in pre-stressing strands in post-tension systems. Determine internal stresses, strains, forces, and deformations for members under any given axial load. I also want you to be able to develop a spreadsheet tool to create axial load versus deformation plots. Explain how pre-stressing affects the axial load deformation response. Formulate a linear elastic uncracked response to approximate behavior. Use this linear elastic uncracked response to relate load to stress, stress to strain, and strain to deformation. Modify these objectives to account for long-term effects for both concrete and pre-stressing steel, so creep and shrinkage and strand relaxation. And use the tension stiffening expressions to include a post-cracking concrete contribution to everything that you developed so far. Pre-stressed members subjected to only axial loads aren't common in practice. We'll examine them, however, because they're a good way to introduce some of our fundamental principles. So for this section, we'll consider an axial loaded member. It can have a combination of a concrete area, pre-stressed area, and non-pre-stressed steel area. And we'll assume that the center of gravity of our concrete is equal to the center of gravity of our steel. So and the center of gravity of our pre-stressing as well. We'll assume that the axial load is collinear with the center of gravity, so we have no moment caused by an eccentricity between the axial load and the center of gravity of our concrete and steel. Because there is only applied axial stresses and no applied moment, our strain profile will be uniform across the cross-section depth. This means the strain in the column will be uniform, so the stress in the column will be uniform, and the stress in the reinforcement and stress in the pre-stressing will also be uniform across the cross-section depth. And we'll assume in this section that plane sections remain plane. We will initially assume that the concrete is initially unstrained and unstressed. This means when our column is subjected to an axial force N, we'll have a strain in the concrete epsilon C. So the total strain in the column will equal the strain in the concrete, which is just equal to the deflection divided by the length of the column. If we have a pure axial load, then the strain in the concrete at the top and bottom fibers will be equal. We can allow for shrinkage, thermal, and creep effects in the concrete by changing how the total strain in the column relates to the strain in the concrete causing stress in the concrete, this epsilon CF. We can add in our shrinkage strain, epsilon SH, and our thermal strain, epsilon CTH, and typically we'll account for our creep by using an effective modulus for our concrete, EC effective. We'll assume that we have a perfect bond between our reinforcing bars and the pre-stressing tendons. We'll talk about a difference between unbonded post-tensioning and bonded pre-tensioning or bonded post-tensioning, but in general we'll assume a perfect bond unless we have unbonded post-tensioning. And then also our non-pre-stress reinforcement is going to have zero strain at the time of casting. So that means that our epsilon S total is equal to the epsilon total, the total strain in our column, which is also equal to the strain in our concrete. We can also take into account the thermal effects similar in the steel, similar to concrete, by adding in this epsilon s thermal term here. Our pre-stress reinforcement, however, does not have the same strain as the surrounding concrete. This is due to the locked-in strain differential between the pre-stressing strands and the concrete. We account for that using this delta epsilon p term. And this delta epsilon p term affects how the strain in our pre-stressing strands relates to the strain in our concrete. This term, this delta epsilon p, will depend on whether we have pre-tensioned or post-tensioned pre-stressing strands. The strain differential will depend on whether we have pre-tensioned or post-tensioned pre-stressing strands. In a pre-tensioned application, the strands are stressed before the concrete's placed, and the strands are stressed to an initial strain, epsilon p sub I. When the concrete's placed, it's cast around the strands, and then after the concrete's allowed to harden, the strands are cut, and the stress is transferred from the strands into the concrete. But at the initial time, before the strands are cut, there's an initial strain in the concrete of 0. So this epsilon ci is equal to 0. In post-tension applications, the pre-stressing strands are tensioned against the concrete. So as this epsilon pi is placed in the pre-stressing strands, the concrete is going to deform. So the initial concrete strain is not going to be equal to 0. We can calculate the locked-in strain differential then by taking the epsilon pi, our initial pre-stressing strain, minus the initial strain in our concrete. And so in pre-tension applications, that initial strain is equal to 0. But in post-tension applications, we'll need to calculate this epsilon ci because, again, the concrete is going to deform as we post-tension the strands against it. We can also add in thermal effects similar to our non-pre-stressed steel and concrete by adding in an additional term here, epsilon p thermal. So that's how we would account for the thermal effects. And typically we'll account for strand relaxation by using an effective modulus for our pre-stressing strands. After casting and anchoring, we'll assume that we have perfect bond, which means that our delta epsilon p will be constant after this point. Our equilibrium conditions are shown on this slide. In general, our internal stresses must balance the external applied loads. So internal stresses are equal to our external applied loads. For our axial loaded pre-stressing members, we'll assume that we can have a concrete component, a steel component, and a pre-stressing component to our internal stresses, and this needs to all be equal to our external applied load. Since the stresses in our axially loaded pre-stressed members are uniform over the entire section, we can just simplify these integrals by just taking the area of our concrete times the stress in our concrete plus the area in our steel plus stress in the steel plus area in the pre-stressing times stress in the pre-stressing. And that'll equal our applied axial load. When predicting our response, we can move from load to stress with our equilibrium relationships, mainly our areas of our concrete, steel, and pre-stressing. We can move between stresses and strains using our constitutive relationships, and we can either use linear elastic relationships or we can use more exact material curves when we move from stress to strains. And then we can move from our strains to our deflections using our compatibility relationships, or mainly the length. Next, we're going to go through an example problem that demonstrates some of the principles that we've been talking about on the last couple slides. We'll look at a square pre-stress post-tension member that has a certain area of our pre-stressing that's stressed to 175 KSI and then anchored. So again, you can note this is post-tensioned pre-stressing. We also have an area of non-pre-stressed steel, and you can see the area of our concrete here. At this point, and we're going to use the ACI material or ACI expression for our concrete modulus of elasticity. At this point, you can pause this video and you can go to the accompanying video for the example problem. In the previous example, we looked at the strain and stresses under certain applied axial loads. We can extend those concepts that we looked at in the previous example and create a complete load deflection curve for our axial loaded pre-stressed member. We can do this by developing or repeating what we did for a variety of different strain levels. For the complete curve, we also need to be concerned with the yield of the materials and when our materials go nonlinear. We'll use this curve here for our concrete. So it's just a pretty standard stress strain curve for concrete. We'll use an elastic plastic, in concrete in tension, we'll assume that we're linear elastic until we crack, and then we'll assume that we lose the tensile capacity of our concrete. Steel, we'll assume an elastic plastic material response. So it's elastic up until yield, and then we'll assume we stay on the yield plateau. We'll use this curve for our pre-stress reinforcement. So pre-stressing in tension, we'll assume that it's linear elastic up until a strain of 0.0086. After this, we'll go nonlinear, and you can see that our stress then will vary with strain. We'll assume that our pre-stressing has no capacity in compression. Typically, pre-stressing strands in compression will buckle, so we'll assume that the stress in the pre-stressing is 0 when we have compression strains in the pre-stressing. The other important points that we'll need the cracking strain, which we can find by just taking the cracking stress divided by our modulus. And we'll also need our yield strain for our steel, again, by taking our yield stress divided by our modulus. You can use any material properties, any material stress-strain relationships that you want for your pre-stressing, for your steel, or for your concrete. And if you're using alternate materials like carbon fiber strands or stainless steel strands, you can substitute in different stress-strain relationships for your pre-stressing strands. On the next few slides, I'm going to walk you through a spreadsheet that I developed for the load deflection curve. Here you can see some of the required inputs. You can see that I'll generally try to separate things out by the concrete component, the steel component, and the pre-stress component. You can see some of the required inputs we'll need here, the column length, the strength of the concrete, these two terms which define your concrete curve, so epsilon naught, the strain at ultimate strength for your concrete, and the assumed ultimate strain in the concrete. After this point, the concrete will fail. And then also the area of your concrete. Here, the yield strength for your steel, the stiffness for your steel, and the area of steel. And then the ultimate stress for your pre-stressing, the yield stress for your pre-stressing, the stiffness of the pre-stressing, the area of pre-stressing, and the initial stress in your pre-stressing strands. With these required inputs, we can calculate some of the initial properties. We can see our initial strain in our concrete, due to the post-tensioning process, the initial deflection in the concrete and the initial stress in the concrete from the post-tensioning, and initial stress in the steel from post-tensioning, and then here the initial force in the concrete and steel from the post-tensioning of the pre-stressing strands. And then here, similar, some of the initial pre-stress properties. We need to do these initial calculations so that we can calculate the locked-in strain differential between the strain in the pre-stressing and the strain in the concrete or in the overall column. So we do these initial calculations to find this number. And if you want more details on how to find these, go back and look again at example problem 1 from this module. On this slide, you can see the actual developed curve where we're relating our strain in the overall column to the force in the column. You can see I highlight some of the significant points here on the right, and we're going from a negative, so a negative strain here is compression and a positive strain here is tension, and you can see some of the significant points. So this epsilon C equals epsilon naught is the strain when our concrete reaches its ultimate strength. The epsilon C equal to epsilon Y is when our steel yields. Here you can see before and after cracking of our concrete. So here the cracking stress and force in the concrete right before it cracks, and then after it all drops off. And then the yield of our steel and the yield of our pre-stressing. You can see I differentiate the three different materials. So we have a column or a series of columns for concrete, steel, and pre-stressing. And in each one of the materials, we have a strain in that material, a stress in that material, and a force in that material. You can see in this example, the strain in the column is equal to the strain in the concrete and equal to the strain in the steel. I have a different column here just so that you can take into account shrinkage, and you can also take into account any thermal effects. You definitely need a different column for your pre-stressing because this column over here, so your overall strain in the column will relate to the strain in the pre-stressing by the locked-in strain differential that we found on the previous slide. So that's the difference there. You can see we use our stress-strain relationships to relate the strain in each material to the stress, and then we use the area of each material to relate the stress to the force component. And then this last column, the axial load, is just the summation of all of our different force components. We can plot the points that we found on the last slide using a scatter plot with straight lines and to connect all the points. Generally, we want to use straight lines so that we're not inferring any points between our two data points that we actually found. So you can see the column behavior is dominated by the concrete material relationship, stress-strain relationship in compression. So you can see that curving off. And then in tension, you can see the point when our concrete cracks and we lose our concrete component. And then you can see the linear elastic response for our steel, and then yielding of steel, and then when we go and we start yielding of our pre-stressing. The amount of pre-stressing will affect our strain or our axial load versus strain diagram. You can see that if we are fully pre-stressed, we'll have a slightly lower axial compression capacity. The pre-stressing puts an axial force in the concrete, so it'll take less additional applied load to fail the concrete. So you can see when we're non-pre-stressed, we have a slightly higher capacity. You can see in tension though, under smaller strains, we'll have a higher capacity. Note that the non-pre-stressed curve will approach these other curves though. So at a higher strain, these will all come together at the same capacity. On the next few slides, we're going to walk through a little more in detail the influence of pre-stressing on our axial load strain curve. The first is that the curve, or our pre-stressing, will cause our curve to be offset from the origin when we have no axial load. So you can see that the pre-stressing is going to cause an initial compression strain in our member when we don't have any axial load. And this is a result of this locked-in strain differential between the pre-stressing and the concrete. Pre-stressing will, however, not have an effect on the tensile capacity of our axial loaded member. You can see that as we get higher strains, the axial load in our pre-stressed member levels out, while the axial load in our non-pre-stressed member is going to continue to increase until they intersect at a higher strain here. Next, we can see that our pre-stressing will increase our cracking load. You can see our non-pre-stressed member is going to crack at a lower load than the member with our pre-stressing. The pre-stressing puts an initial compressive stress in the concrete, and this initial compressive stress needs to first be overcome before cracking can occur. So you can see we'll need a higher axial tension load to cause cracking in the concrete in the pre-stressed column than in the non-pre-stressed column. Pre-stressing will also reduce the concrete tensile strain at service load. You can see here, if we assume that our service load is right around this level, you can see in the non-pre-stressed member, we'll have a higher concrete tensile strain, or the tensile strain in the column than in our non-pre-stressed member, where we can actually have a axial tension and we can still have compression strains in the column. So this is, again, because of the locked-in strain differential between the pre-stressing and the concrete. Finally, as mentioned, the pre-stressing will reduce the compression capacity and stiffness a little bit for our pre-stressed concrete column. This is because the pre-stressing adds compression before any load's applied. This means that there's less applied compression required for the concrete to reach its ultimate strength. So typically this is a minor effect, but it is a consequence of using pre-stressing. Next, we're going to look at how we can account for time effects in our axial loaded pre-stressed concrete columns. And to do this, we will discuss the difference between a short-term response and a long-term response. Our entire previous discussion was a short-term response, not including the time effects or time-dependent properties for our concrete, steel, or pre-stressing. Our long-term response, we need to consider the time-related effects, and this includes creep, shrinkage, relaxation, and also any thermal effects we can include. First, we can account for our shrinkage and thermal strains directly in our compatibility equation, relating our total strain in our column to the strain causing stress in the concrete, plus our shrinkage strain plus our thermal strain in the concrete. We can account for creep using the effective modulus for our concrete. And to do this, we'll modify we'll have our effective modulus for our concrete, which is just the modulus divided by 1 plus our creep coefficient. And we can use this effective modulus everywhere where we use the modulus before. So we can use that when we determine the strain at ultimate stress. So use the effective modulus there. And we can also use the effective modulus to relate the stress in our concrete to strain when we're using the linear expression in tension. For our non-pre-stress reinforcement, we can again include our thermal strains in our compatibility relationship, just relating the total strain in the column to the strain causing stress in our non-pre-stressed steel plus the thermal strains in the steel. We can do the same thing with our pre-stress reinforcement, including our thermal strain component there. And we can also include the strand relaxation by using the effective modulus. And a lot of times we'll have relaxation in terms of a percentage, and we'll just modify the strand modulus by the percent relaxation. So for an example, if we have 5% strand relaxation, then the effective modulus in our pre-stressing strands will be 95% of the normal modulus for our pre-stressing strands, E sub P. Next, we're going to look at how we can account for these time effects using the same example that we did for example 1. So it has the same cross section, the same area of pre-stressing, the same area of concrete, same area of non-pre-stress reinforcement, and the same initial stress in the pre-stressing. You can see we're going to include some time effects. So we'll include a creep coefficient of 2.7, a shrinkage strain of -0.4 times 10 to the negative third, and 5% strand relaxation. We would find these values just using any shrinkage and creep and relaxation equations that we'd like. So similar to what we talked about in previous modules. So at this point, you can pause this video and you can go to the video going through example problem 2. As we did for our short-term response, we can also generate a complete axial load strain response for our column, including our long-term effects, or our time effects. So here we can see a short-term curve and a long-term curve. And on the next couple slides, we'll kind of step through the effects of our long-term effects on the response of the column. The first effect that we can see is the strain under 0 applied axial load is going to increase over time. So you can see as the column is just sitting with no applied axial load, it's going to increase in strain. This is primarily due to the creep and shrinkage of the concrete. So you can see we're increasing in strain under no applied axial load. This axial shortening needs to be accounted for in your design. The next observation is our time effects are going to influence the behavior of our non-pre-stressed reinforcement. So under our long-term loading, the yielding of our rebar in compression is going to occur much sooner than under our short-term loading. And that's because our creep and our shrinkage are going to cause a compression load that's transferred to the reinforcing. So I kind of lay out what this is in the figures that you see here. So if we look at a typical reinforced concrete column, we would have concrete and we would have our steel reinforcement. If we have no reinforcement, our column would shrink and creep to a certain point. So you can see the unrestrained deformation is highlighted here. What happens is when you add steel in, that steel is going to resist this unrestrained deformation. So in the restrained case, or the reinforced concrete case with steel and reinforcement, we'll have less deformation than in the unrestrained case. And the steel here resisting this deformation is going to cause the steel to go into compression. So you can see these compressive stresses are going to cause the steel to yield in compression much sooner than if we have no time effects considered. The next effect that we can see is our ultimate compression strength is going to slightly increase if we include our long-term effects. This is because the pre-stressing, so you can see short-term here and long-term there, so a slight increase in our ultimate compression capacity. This is because some of our pre-stressing stresses will be lost as our column creeps and shrinks and the strands relax. So there's less pre-compression, so that means there's slightly higher compression capacity in the concrete. Next, we can look at the ultimate strength in tension. Generally, the tensile capacity will not be influenced by our time effects. And this is just because the yield strengths are what they are. And the yield strengths and ultimate strengths of our steel material are pretty set. So the yield strengths of the material control the tensile the yield strengths of our steel and pre-stressing control the capacity and tension. Because those aren't affected by time effects, neither is the overall tensile capacity of the column. And finally, you can see that the stiffness in compression is going to be much smaller when we take into account our time effects. And this is because the stiffness of our short-term curve is dependent on just our modulus EC, and the stiffness of our long-term curve in compression is primarily dependent on the effective modulus. And the effective modulus is less than the modulus for our concrete, so the stiffness decreases when we take into account our long-term effects. Shown here is the long-term and the short-term curves for the column that we've looked at in the previous examples. And you can see some of the points that I've pointed out on the last few slides. You can see here in the difference between the short-term and the long-term responses. So far, we've looked at the complete response, the complete axial load response of our columns using the more exact material stress strain curves. And you can see that this can be a difficult process and can require a spreadsheet or longer hand calculations. You can see that there is a large linear elastic range between when our concrete cracks and when our concrete starts to go nonlinear. So we have a large linear elastic range. So we can use linear approximations to model our column for a kind of a large load range. And we'll keep our concrete uncracked. That'll be the top, kind of the top end of our linear range. And then the bottom range will be kind of when our material properties will still be linear elastic. So before we have yielding in our steel or pre-stressing, and before our concrete starts to go nonlinear. When we look at our linear elastic response or linear approximation, nothing changes with our equilibrium equation. We still have our externally applied load equaling our component of internal components, so concrete, steel, and pre-stressing. Nothing changes with our compatibility equations. We can still find our strain in the concrete equal to strain in steel, or strain in pre-stressing equal to strain in steel plus the locked-in strain differential for short term, and we can account for our long-term effects the same way with our compatibility equations. The difference in the linear elastic approximation is with our constitutive equations. We'll assume that we have a linear elastic response for our concrete, our steel, and our pre-stressing. This means that we can relate the strain in our concrete that causes stress to our stress just by the stress in the concrete, just by the modulus. And we can assume these this modulus for concrete, for steel, and for pre-stressing. And again, in the linear approximation, we are assuming that we have a linear elastic material relationship. So if we calculate our stresses, we need to actually check this assumption in our analyses to make sure that our assumptions are valid. We can combine the three sets of relationships that I showed on the previous slide to get a direct relationship between the strain in the column and the axial load. This equation can be a little messy in terms of formatting, so we can simplify it by defining two additional parameters. The first is this n sub naught. This n sub naught is called the decompression force, and this is essentially the force required to produce zero strain in the concrete. We know that our pre-stressing is going to cause a compression strain in the concrete under no axial load. So this force is the force required to kind of take that strain out. So to get back to zero strain. You can see if we're just considering our short-term effect, we just have this first term, but we can also include our long-term effects in terms of our shrinkage and our thermal effects by adding these additional terms. The other property that we'll need is our transformed concrete cross-sectional area, this A sub transformed. And this is just, we're transforming our area of steel and our area of pre-stressing into an equivalent concrete area using the modular ratio, or the ratio of our modulus for our steel to the modulus of concrete and modulus of our pre-stressing to the modulus of the concrete. as shown here, this would be for short term. We can also include our long-term effects by modifying or by using EC effective and by using EP effective in this equation. Using these new variables, we can then write this equation here, relating the strain in our column to the applied axial load. So it's a, a direct linear equation here. And as I said, it's valid between when the concrete cracks in tension, so the tensile strength of the concrete, and when the concrete starts to go non-linear in compression. And typically this will be about 0.5 F prime C, maybe 0.6 or 0.7. It varies a little bit, but anyway, it'll be somewhere in the 0.5 to 0.7 times F prime C range. And again, you can see our N naught, our decompression force, and our transformed area defined here. At this point, we're going to use the equation that we found on the last couple slides in an example. This will be the same cross-section and the same example that we've been working through in this module with the same initial properties that we found before. And we're going to solve and compare our strains and stresses for these 2 points. So an axial tension of 225 and an axial compression of negative 1,000 kips. So at this point, you can pause this video and you can go to the video walking through example problem 3. Next, we're going to look more closely at the post-cracking concrete tensile response. So up to this point, we've assumed that after the concrete cracks, we have no contribution from our concrete. So we're assuming that our concrete essentially disappears after it cracks. In reality, the concrete's going to continue to make a contribution to the overall behavior of our column even after it cracks. And this is due to the bond between the concrete and the reinforcement. So if you look at the axial load versus strain plot for our column, we can see if we had a bar alone, we would have a linear elastic response until we have yielding of the bar. If we have the bar embedded in concrete, then we would have a linear elastic response up until we crack the concrete. And then at this point, we would have kind of a curvy transition between the point here when our concrete cracks and the point here where our steel yields. And this difference between this line of the bar alone and the kind of actual behavior of the bar embedded in concrete is commonly called tension stiffening, or you can say the difference is due to the tension stiffening effect. When we're talking about tension stiffening, we need to distinguish between the average and local conditions. The average condition is the condition of the entire member. So it's the average response of the entire bar embedded in concrete. The local condition, however, is the condition locally at a crack. At a crack, there's no concrete present because you're at a crack. So you just have your steel. But overall, you have your concrete surrounding your steel. So you'll have the average response versus local response. We only include tension stiffening when we're talking about the average response or average condition. And with the average condition, we can obtain the average strain over the length of the column by just taking our deflection divided by the overall length. The average stress in the concrete we can find by adding on this additional component that I'm highlighting after the concrete cracks. And we can use the equation shown here where it's a stress-strain relationship where we have an alpha 1 and an alpha 2 factor based on the bond characteristics and the load type. Here you can see the alpha 1 factor depends on if we have deformed bars or plain bars, wires, or bonded strands, or if we have unbonded reinforcement. And our alpha 2 factor depends on if we have short-term or sustained or cyclic loading. So we can use these alpha factors and we can use this stress strain response in our spreadsheets that we developed to include the effects of tension stiffening. Since we're taking into account our tension stiffening in our concrete stress strain relationship, we can use the same stress strain relationships for our steel and our pre-stressing as we did before. And our equilibrium equation is still true. That doesn't change. Now, our local condition is at a crack. So at a crack, we don't have any concrete here. So we assume that our concrete stress is equal to 0. And because of this, our reinforcement that's crossing the crack needs to pick up the entire load in the column. Our reinforcement is the only thing contributing to the strength of the column at the crack. Because of this, at our local condition, we have this additional strain at the crack that's going to increase the stress in the steel and the stress in the concrete. So we can still use our equilibrium equation, but now we can solve for the additional strain component by, I guess, adding it to our stress-strain relationships and plugging them in here. So we can solve for our incremental strain, and then we can also solve for our stress in the steel and stress in the pre-stressing at the crack. So these stresses are going to be higher at the crack than they will overall in our average response. At this point, we'll look at how we can include tension stiffening into our analyses using an example problem. We're going to use the same example problem that we've been using, this 18 by 18 inch column with the same area of pre-stressing in steel and concrete, except now we're going to look at our axial force, our average stresses, and our local stresses at a crack under a forced displacement here of 1/8 inch. So we'll include the tension stiffening response in our average stress, and then we'll look at our local response at a crack here as well. You can pause the video now and you can go to the accompanying video for example problem 4. On the next few slides, we're going to look at how we can include tension stiffening in our load deformation response. So you can see here from before our load deformation response not including tension stiffening. And you can see the ultimate capacity and tension is 568.3 kips. We know that our tension stiffening cannot increase the capacity of our column past this value, because if it does, then we'll have failure at a crack. Here you can see the load deformation response including tension stiffening. So here you can see before and after cracking, which on the previous slide, after cracking, our stress in our concrete went to 0 and continued on to 0. Here, when we include the effects of tension stiffening using the equation that we looked at a few slides ago, you can see that we'll still have some contribution of the concrete to our capacity. And you can see here that the strength of our column, if we include tension stiffening without any modifications, will increase and will be higher than the strength that we found on the previous slide without tension stiffening. So we know that tension stiffening cannot increase the capacity of our column. Tension stiffening only stiffens the column. So we need to modify this manually so that we will get the correct response of our stiffened column without an increased capacity. The correct way to apply tension stiffening is to include tension stiffening until you reach the cap. So the axial load capacity of the column without tension stiffening, only including the steel components. So here you can see that we reached the previous cap that we found 2 slides ago, 568.3, And once we reach that cap, we no longer include the tension stiffening component. So here we would calculate the stress in the concrete based on the axial load cap here. And then here we have our tension stiffening no longer contributes because we're at the cap. The data from the previous slides is plotted on this slide. You can see the local response without tension stiffening, the response with tension stiffening applied incorrectly, so allowing for an increase in strength, and then also the response applied correctly where the tension stiffening stiffens the member, but then is capped by the tensile capacity, including only the non-prestressed and prestressed steel. We can include the long-term response in tension stiffening just by using the effective modulus rather than, or wherever we used EC. The effective modulus for our pre-stressing, wherever we used the pre-stress modulus, and our alpha 2 factor will be 0.7 rather than 1.0. And you can see how that will change you can see the difference between the long-term and the short-term response, with tension stiffening. Next, we're going to look at the relationship between crack widths and crack spacing. In cracked reinforced concrete, our elongation is going to be made up of our discontinuous separation at the cracks, so what happens at the crack, and then strains between the crack. In general, the discontinuous separation at the crack is going to be much larger than the straining between the cracks, so we'll typically ignore the straining that happens between cracks in our crack width calculations. On the next couple slides, we're going to consider a column with length L that deforms a distance delta, and therefore we can calculate the average strain over the length as just the delta divided by L. We can then define S sub m as the mean crack spacing and W sub m as the mean crack width. We can, with these definitions, the number of cracks over the distance n is just the length divided by that mean crack spacing, so L over S sub m. And our total deformation, which will be accounted for by the cracks, so delta, will be equal to the number of cracks times the crack width. And this again is based on the deformations being concentrated at the cracks and not between the cracks. So modifying this equation, we can have our crack width equal to delta, or total deformation, divided by n. We know that delta is equal to the strain times length, and n we found to be equal to L divided by the mean crack spacing. So we can get this equation here, and then simplifying it, we can see the direct relationship between crack width and crack spacing. So the larger the spacing between the cracks, the wider the cracks will be. The average crack spacing is going to be related to where the reinforcement is in relation to the edge. This Cmax term is defined as the maximum distance from the concrete fiber in tension to the nearest reinforcement. So here, this point right here is the furthest point from any reinforcement. So our Cmax is the distance between that and the closest reinforcement. The shorter, I guess the closer the edge is to reinforcement, the closer the cracks. So a smaller Cmax will mean a smaller crack spacing. So in general, we want to keep some reinforcement close to the edge of our concrete member in tension, and this will help us to have closer cracks, which means the cracks will be smaller. In general, we want smaller, more closely spaced cracks, which will make our member more durable if it does crack. Note there are more accurate expressions available. So I highlight two of those here at the bottom. On this slide, I wanted to highlight that there is a minimum reinforcement required for crack control. Essentially, we need to provide enough reinforcement so that when our pre-stress member cracks, it doesn't immediately fail. So here, if our NCR is greater than NY, so our cracking axial load is greater than our yield axial load, as soon as our specimen cracks, it'll fail because it can't hold any more weight. So we need to make sure that we have enough reinforcement so that after cracking, we have a greater yield capacity of our column. Cracking helps us to know, or cracking helps us to give us warning of a failure. So if we don't want our beam to, or our column to crack and immediately fail. I give some general relationships for pre-stress members to prevent this. Note these are just general relationships, and when we talk about flexural members, we'll look at actual code expressions for this minimum reinforcement requirement. This concludes this lecture on the responsive members to axial load.